Imagine you're trying to train a large language model, an LLM, to do something really complex, right? Like uh, solving advanced math problems, or maybe writing some pretty sophisticated code.
Yeah, they're really tough stuff.
Exactly. And the way we've often done this using reinforcement learning, or RL, it kind of gives the model a simple, yep, you got it, or nope, wrong signal, but only at the very end.
That's the sparse reward problem. You only get the pat on the head if you manage to stumble across the perfect final answer.
Which makes it incredible.
Well, what if instead of asking the AI to just blindly solve a problem for that final reward, we asked it to be a teacher?
A teacher.
Yeah, an AI teacher that's given the solution up front. Its job isn't solving, it's explaining. It gets rewarded based on how well it explains that solution step by step to a student AI.
Ah, I see. So the focus shifts.
Exactly. And that's the really fascinating idea behind these reinforcement learned teachers, or RLTs.
So today we're doing a deep dive into some new research introducing these RLTs. We're going to unpack why this shift, which sounds kind of simple from solving to explaining, is actually causing these big aha moments in AI.
And leading to some pretty surprising performance gains, often outperforming much bigger systems.
Right. And crucially, how this could potentially, you know, democratize AI development a bit more. You'll see how maybe a simpler framing of the problem is unlocking some serious capability.
Let's get into it.
Okay, so to really get why RLTs are a big deal, let's quickly revisit the landscape. What were the standard ways people tried to train reasoning in LLMs before this?
Well, the main approach was what you mentioned, RL reasoning. Things like DeepSeek R1 really popularized this. The goal was always to get the model itself to figure out complex reasoning paths for, yeah, high-level math, coding, that sort of thing.
Trying to make the model think step by step.
Exactly. But the huge hurdle, especially with those one-hot correctness rewards, it's either 100% right or 0% right, nothing in between.
Right, the sparse reward problem again.
Yeah, that's the exploration challenge. The model gets basically no useful learning signal, no gradient, unless it can already solve the task with some initial chance. It can't really bootstrap its way up from partial understanding.
It's stuck if it doesn't know where to even start looking.
Precisely. And the consequence, as you hinted at, is usually only the very biggest, most capable models actually improve consistently this way. Smaller models just spin their wheels.
Okay, so that difficulty led to something else, right? This teacher-student idea.
Yeah, the teacher-student paradigm kind of emerged from that. People realized these big RL-trained models often weren't the ones getting deployed directly. They were too big, too expensive to run.
So instead, they acted as teachers.
Exactly. They became teachers to distill their knowledge, their reasoning steps or traces, into smaller, more efficient student models. That way you get the reasoning power, but in a more manageable package.
Makes sense. But you're saying there was a disconnect there.
A big one. The surprising thing is the skills reinforced by just trying to get the final answer right, well, they aren't necessarily the best skills for teaching someone else how to get the answer right.
Ah, okay. Solving isn't the same as explaining.
Not at all. And this misalignment meant that the whole pipeline still needed a lot of expensive, often manual or heuristic-driven post-processing. You'd take the raw output from the giant teacher model.
The reasoning steps it generated.
Right, and you'd have to clean it up. Filter out confusing parts, maybe reorder steps, simplify things. Basically, a human editor tidying up the AI's thoughts before they could be effectively used to train the smaller student model.
That sounds really inefficient.
It is very resource intensive.
Which I guess brings us perfectly to the core idea behind these reinforcement learned teachers, the RLTs. It feels more intuitive somehow.
It really does. Think about a great human teacher. We don't measure their greatness by whether they can invent calculus from scratch on the blackboard, right?
No, of course not.
We measure them by their ability to take established knowledge, the solutions, the theorems, and craft these clear, step-by-step, insightful explanations for their students. It's about clarity, guidance, logical flow.
Okay, so RLTs try to capture that ability in an AI.
Exactly. They formalize it. So unlike traditional RL, where the model is just given a question and has to figure out the answer from scratch,
The think and solve approach.
right, RLTs are different. They are prompted with both the question and the solution. Ah, okay. They get the answer key up front.
Precisely. Their task isn't finding the answer, it's connecting the dots. Generating a detailed step-by-step explanation that logically leads from the question to the provided solution in a way that's tailored for a student model to understand.
So, using your earlier analogy, it's like giving the AI the riddle and the answer, and its job is to explain how that answer makes sense, step by step.
You got it. And the immediate huge advantage here is that this completely sidesteps that massive exploration challenge from traditional RL.
Because it always knows the target.
Exactly.
Yeah.
The RLT always has the correct answer, so it can always get a useful learning signal. It's not fumbling in the dark anymore. It sees the destination and learns how to best guide others there.
Okay, that makes a lot of sense intuitively, but how does it actually learn to be a good teacher? What's the mechanism, the reward?
Ah, yes, the secret sauce.
Yeah.
The reward system for RLTs is really clever. It's designed to be inherently dense.
Dense meaning.
Yeah.
It gets feedback constantly, not just at the end. Exactly. Rich, informative feedback all the way through the explanation process, even before the RLT is an expert explainer. It's the opposite of those sparse all-or-nothing rewards.
Okay, so how does this dense reward work? What goes into it?
It basically relies on two key parts, two reward terms. The first one is called RSS. That stands for Student Understanding.
Student understanding. Oh.
This part measures how well the student model actually understands the solution after seeing the teacher's explanation. Technically, it looks at the student's log probabilities for the tokens in the correct solution.
Log probabilities, like how confident the student model is in predicting the correct answer sequence, given the explanation.
You've got it. It ensures the teacher's explanation genuinely leads the student to be confident about the right answer.
Okay, that makes sense. What's the second part?
The second term is, I think, particularly cool. It's RKL, which stands for Explanation Clarity in the Student's Mind.
Explanation clarity.
Yeah.
Using KL divergence. How does that work?
Right. It uses KL divergence, which is a way to measure how different two probability distributions are. Here, it measures whether the teacher's explanation steps, the think tokens, seem like logical, interpretable next steps from the student model's perspective.
Whoa, okay. So it's checking if the explanation actually makes sense to the student, not just if it gets to the right answer eventually.
Exactly. It prevents the RLT from just, say, repeating the solution over and over, or generating steps that are correct but completely unlearnable or non-intuitive for the student. It forces the explanation to be coherent and, well, teachable.
So putting those together, RSS makes sure the explanation leads to the right answer, and RKL makes sure the path taken by the explanation is logical and understandable for the student.
Precisely. The combined reward, RRLT, Israel's RSS, RKL, where lambda is just a weighting factor, pushes the RLT to generate explanations that are not only correct, but also genuinely instructive. It has to show its work in a way the student can actually follow and learn from.
That feels crucial. It stops the teacher from just finding clever shortcuts that don't actually help the student learn the reasoning.
Absolutely. It's about effective knowledge transfer, not just finding any path to the solution.
Okay, the theory sounds really promising,
Yeah.
but does it actually work? What about the performance? This is where it gets interesting, right?
Oh, this is where it gets really interesting. Almost a David versus Goliath situation, like you said. The core finding, the really surprising one, is that the raw outputs no post-processing needed from a relatively lightweight 7 billion parameter RLT.
7B, that's pretty small these days.
Tiny compared to the giants, yeah. This 7B RLT delivered significantly higher performance on really hard tasks. Competition math like AIM, graduate level stuff like math and GPQA, compared to existing pipelines.
Pipelines using those massive reasoning models.
Exactly. Pipelines using models like DeepSeek R1, which is, 671 billion parameters, orders of magnitude larger. And those big models still needed that expensive heuristic post-processing we talked about.
Wow. Do you have any specific numbers?
Yeah. For instance, the paper shows the 7B RLT hitting an overall score of 49.5% across these benchmarks. The comparison system, using process traces from the giant R1 model to train a 7B student, only got 46.6%.
It's actually a pretty significant jump, especially considering the size difference and the lack of post-processing for the RLT. Huge win for efficiency.
It really is. And what's perhaps even more impressive is the scalability. This RLT approach holds up even when you use it to train larger student models, say 32 billion parameter ones.
So it's not just good for small models.
Nope. An RLT-trained 32B student achieved 73.2% overall, beating a comparable 32B student trained using the process traces from the giant model, which scored 71.5%.
Okay, so this RLT method seems genuinely better at the distillation process itself.
It strongly suggests that, yeah. It indicates that RLTs could help us overcome those huge costs associated with traditional RL reasoning. You shift the complex RL part to these smaller, specialized RLTs, it could really democratize access to high-performance AI reasoning.
That's a big claim. What about other benefits? Does it help with starting new training runs?
It seems so. The research mentions RLTs providing better cold starts for traditional RL training, too.
Meaning, if you do want to run traditional RL afterwards, starting with an RLT trained model gives you a better head start.
Exactly. The data showed that combining an RLT 7B teacher with subsequent RL training led to better results, 50.53% overall, than starting RL from other 7B teachers, even ones whose outputs were cleaned up using GPT-4.
So it provides a stronger, more stable foundation if you want to build on it further.
Seems that way. It makes the whole process potentially more robust.
Okay, efficiency, scalability, better starting points.
Yeah.
What about flexibility? How well does this generalize? Can an RLT trained on math teach something else?
That's another really intriguing finding, the zero-shot transferability. They took RLTs trained purely on math and coding problems and applied them zero-shot, meaning no extra training for the RLT itself, to a completely different kind of task, something called the countdown task, which is more about number manipulation and arithmetic reasoning.
Check do.
Remarkably well. The RLT, without any specific training on countdown, was still able to generate effective explanations that could be used to distill knowledge into a student model for that task.
Wow.
Yeah, applying the RLT distillation zero-shot achieved a score of 49.2%, which was actually pretty close to the 50.8% achieved by training a model with DirectRL specifically on the countdown task itself.
So the teaching skill itself seems to transfer across domains.
It suggests a strong level of generalization in the learned explanation strategy, which is incredibly promising.
And just to be sure this isn't all smoke and mirrors with the reward function, did they check if the RLT's own reward score actually correlates with how well the student learned?
They did, and they found a very clear, strong correlation. The Pearson coefficient was over 0.89.
Okay, nearly 0.9, that's high.
Extremely high. It basically confirms that the RLT reward function, maximizing student understanding while ensuring clarity, is directly and effectively driving better learning outcomes for the student model. It's not just a theoretical idea, it demonstrably works.
And this holds up on other types of tasks too, like more coding or different languages.
Seems so. The paper mentions consistent performance from RLT distilled students on benchmarks like Live Code Bench for coding, and even multilingual math benchmarks like Olympiad Bench.
Okay, so across the board, for 32B students especially, the RLT approach seems to be outperforming the previous state-of-the-art distillation methods.
Consistently, yeah. For instance, on those diverse benchmarks, RLT distilled 32B models scored around 67.6%, whereas the bespoke 32B, using the Process Giant model traces, got about 65.7%. It confirms the broad applicability.
That's really compelling evidence. So let's dig a bit deeper into why it works so well. You mentioned those two reward terms, student understanding, RSS, and explanation clarity, RKL. How crucial are both of them? Did they try taking one away?
They did exactly that through ablation studies, basically removing parts of the system to see what breaks.
Yeah.
And the results really highlight why both terms are needed.
Okay, what happened when they removed RKL, the explanation clarity part, the bit that checks if the steps make sense to the student?
That had a dramatic effect. Without RKL, the RLT basically lost the ability to tell the difference between an explanation that genuinely guides the student step by step versus one that just kind of games the system to boost the probability of the final answer without a clear logical path.
So it couldn't tell if it was actually teaching or just, I don't know, hinting very strongly.
Pretty much. It led to the RLT taking shortcuts. It started just repeating tokens from the solution within its explanation, because that technically increases the student's likelihood of predicting the solution, but it doesn't teach reasoning.
Did that affect the explanations?
Hugely. The average explanation length plummeted from over 6,300 tokens down to just about 1,300. It just wasn't explaining much anymore.
And the student's performance, that's the real test.
It crashed. Student performance actually dropped below the baseline score of the original untrained student model. It went from a baseline of 39.17% down to 34.90%.
Wow. So removing that clarity term made the teacher actively worse than useless.
Effectively, yes. It powerfully demonstrates that RKL is absolutely essential. It's what forces the explanation to be genuinely learnable and logically sound. It stops the RLT from just, well, cheating.
That's crystal clear.
Okay.
What about the other tweak they mentioned, removing the min-max reductions in the reward calculation? What did that do?
Removing those normalization steps also had a noticeable, though less catastrophic, effect. The reward calculation became biased by the sheer length of the explanation.
So longer explanations got better scores, regardless of quality.
Not quite. The RLT started preferring really long explanations, apparently as a way to sort of dilute the negative impact of any single difficult or perhaps less clear step on the overall RKL score.
Ah, so it padded the explanations.
It seems so. It led to overly long, sometimes repetitive explanations. The average length ballooned from that 6,380 token baseline up to over 8,850 tokens.
And performance. Did it hurt student learning?
Performance was still decent, actually 47.43%, which is good, though not quite as good as the full RLT's 49.50%. But it was much less efficient, both in terms of training the RLT and the length of explanations it generated.
So every component of that reward function seems carefully tuned and necessary for getting that sweet spot of effective and efficient teaching.
It really appears to be a well-designed system where each part plays a critical role. It's a delicate balancing act.
Okay, this sounds incredibly promising, but like any research, there must be limitations or areas still to explore.
Oh, absolutely. And the researchers are upfront about them. One key thing is that RLTs, in your current form, still need access to those ground truth solutions.
Right, the answer key, which might not always be available, especially for brand new problems.
Exactly. Finding or generating those solutions can be a bottleneck in itself for some domains. Also, there's still an initial supervised fine-tuning step needed before the main RLT training begins.
So you need some initial examples of good explanations to get the RLT started.
Yeah, a small set of pre-collected examples seems necessary to kind of bootstrap the RLT's basic explanatory abilities. And technically, the current setup uses a separate student model just for calculating the reward during the RLT's training.
Does that add much overhead?
They note the computational cost is pretty minimal in practice, especially compared to training giant RL models, but it is a distinct component in the architecture. These are definitely areas for ongoing work.
Makes sense. But the potential future directions they mentioned sound really exciting.
They really do. Imagine if the teacher and student could be trained together, in tandem.
So the teacher's explanations could adapt in real time based on how the student is actually learning, like a responsive tutor.
Exactly. A truly dynamic teaching process. And pushing it even further, could the same AI model potentially play both roles?
Generate an explanation and then learn from its own explanation. Self-distillation.
Yeah. That could potentially unify the open-ended exploration benefits people seek from RL with the stability and data efficiency of supervised learning. It's a fascinating prospect.
And we've mostly talked about the results with 7B RLTs. What happens if you scale the RLT itself up?
That's another huge open question. Given how well the 7B worked, imagine the potential explanatory power of a much larger RLT, say 70B or more, focused purely on generating high-quality, distillable reasoning. The potential seems enormous.
So stepping back, what's the big picture impact here? You mentioned democratization.
I think that's key. RLTs genuinely seem to promise a way to make training highly capable reasoning models more accessible and much more efficient.
By shifting the really heavy lifting of RL onto these smaller, specialized teacher models.
Precisely. It lowers the barrier to entry. Instead of needing colossal compute to train a giant reasoning model from scratch, you could potentially train a smaller RLT and use it to distill powerful reasoning into more manageable student models. This could empower more researchers, more organizations, maybe even individuals, to leverage advanced AI reasoning.
Which could help tackle bigger challenges.
Potentially, yes. Making these capabilities more widespread could accelerate progress in many fields.
So to wrap up for everyone listening, what's the core takeaway here? The RLT idea really flips the script, doesn't it?
It absolutely does. Instead of focusing on the struggle of solving, it focuses on the art of explaining. And somewhat counterintuitively, this focus on teaching seems to unlock better performance, especially when it comes to transferring knowledge efficiently to other models.
And it's achieving this with smaller, more efficient models, bypassing a lot of the cost and complexity of older methods.
Right. Which leads to a really interesting thought to leave you with. Could it be that the ultimate measure of an AI's intelligence isn't just about what it knows or what problems it can solve in isolation, but how effectively it can teach what it knows? How well can it transfer its understanding to others, whether AI or maybe even eventually to us?
That's a fascinating question. Makes you think about learning itself. How do you learn best? Would you prefer an AI that just spits out the right answer, or one that can genuinely walk you through the why and the how?
That ability to explain, to guide understanding, that's the real power the reinforcement learn-to-teacher concept is tapping into.
And it feels like we're just scratching the surface of what's possible here. Definitely something to keep an eye on.